Einstein and Bohr engaged in several scientific conferences, especially at the Solvay conferences of 1927 and 1930, where they debated the nature of quantum mechanics. These discussions were philosophically and scientifically significant as they presented differing views on how to understand physical reality. Einstein believed that quantum mechanics was incomplete and that there should be a more complete theory, while Bohr defended the Copenhagen interpretation and believed that nature is inherently probabilistic. The following is a reconstruction of the dialogues between these two scientists based on historical records and documented accounts from the Solvay conferences. So please like the video, subscribe to the channel, and turn on the notification bell so we can dive straight into this fascinating debate between two geniuses of physics.
Dr. Bohr, I cannot accept that quantum mechanics is a complete description of physical reality. While this theory has provided remarkable results, it is merely a computational tool and does not give an accurate picture of the world.
But Professor Einstein, experimental results have shown that quantum mechanics is a very successful theory. Principles like Heisenberg's uncertainty principle, the probabilistic nature of the wave function, and its collapse upon measurement have all been confirmed through experiments.
Nevertheless, a theory that only provides probabilities and cannot explain what really happens is not satisfactory to me. I believe there must be hidden variables that quantum mechanics is unaware of.
But physics is about describing what we can observe. If we cannot directly measure something, how can we include it in the theory? We cannot talk about reality beyond what is measured.
Are you saying that something that cannot be observed does not have reality? This is an extreme view. Imagine if the moon only existed when we look at it.
That's an incorrect comparison. On a quantum scale, observation and measurement are inseparable from the system. The moon is a macroscopic object, but in the world of subatomic particles, we cannot observe something without altering the system.
Let me propose a thought experiment. If an electron passes through a screen with two slits and we determine its path, the interference pattern disappears. But if we don't determine its path, the interference pattern is observed. Does this mean that our observation changes reality?
Yes, this shows that the act of observation has a direct impact on reality. When you determine the path of the electron, its wave-like nature disappears and it behaves like a particle. When the path is not observed, the wave-like property is preserved and the interference pattern appears. This is an intrinsic feature of quantum mechanics.
So you are saying that reality depends on measurement? This is unacceptable to me. Nature must exist independently of the observer.
But numerous experiments have shown that these limitations are real. The uncertainty principle shows that we cannot simultaneously measure the position and momentum of a particle with unlimited precision. This limitation is not a flaw. It is part of nature.
The double-slit experiment is one of the most significant thought experiments in the history of quantum mechanics. In this experiment, an electron passes through two slits and leaves an interference pattern on a screen behind, similar to what a wave could create. If we measure the electron's path, the interference pattern disappears and the electron behaves as a particle. This result led Bohr to realize that measurement and observation are inherent to the quantum system. In this way, Bohr defended the principle of probabilistic predictions in quantum mechanics.
Dr. Bohr, let's imagine a box filled with photons. This box has a clock and a small opening that can be briefly opened to let a photon escape. Now, if we precisely measure the time the photon escapes, we can also determine its energy. In this way, we have bypassed the uncertainty principle, as both energy and time are measured with unlimited precision.
Professor Einstein, you have overlooked one crucial point in this experiment. If we weigh the photon box to determine that a photon has escaped, this measurement will cause a tiny change in the position of the center of mass of the box. According to your theory of relativity, this change will lead to an uncertainty in measuring time. Therefore, Heisenberg's uncertainty principle still holds.
So, you used my theory to prove the validity of quantum mechanics?
Yes, it seems that the uncertainty principle is inviolable.
The photon box thought experiment proposed by Einstein was designed to challenge Heisenberg's uncertainty principle. He argued that if we simultaneously measure both the time and energy of a photon, we could seem to violate this principle. Bohr's response was to point out that, based on a special relativity, measuring the position and time of the photon would lead to small changes in the system. This showed that measurements always involve small alterations in quantum systems, which themselves create limits to measurement accuracy. After these discussions, Einstein still believed that quantum mechanics was incomplete and that hidden variables must exist. However, Bohr and the proponents of quantum mechanics believed that the theory provided an accurate description of reality, even if it seemed counterintuitive. In the following years, scientific experiments like the Bell experiment showed that Einstein's view on local hidden variables could not be correct, and quantum mechanics predictions were confirmed. Nevertheless, this debate remains one of the most important and fascinating scientific discussions in the history of physics. This debate was not only about the philosophical challenges between Einstein and Bohr, but also became the foundation for one of the greatest scientific discussions in the history of physics. Ultimately, Bohr's views on quantum mechanics were confirmed through scientific experiments, but Einstein continued his research for a more complete theory. This debate profoundly impacted the development of quantum physics and the philosophy of science, and remains one of the most engaging and insightful discussions in the history of science. Until our next video, farewell.